Since the first semiconductor chip was built in the 1950s, computing power has increased exponentially while cost and size have plummeted. But lately, we've hit a slump. Moore's law, once the golden rule for computing, is losing its grip. We aren't doubling processing power at the same rate anymore, and a big part of the problem is the tech itself.
We've known for, many years, decades, that the current way in which we manipulate information and compute, that is the digital approach, has its limitations. There are limitations to the types of problems that classical digital computers can solve.
Now, a race of global proportions is taking shape, all in pursuit of something that will kickstart a new technological era. We're talking about the race to build the world's first functioning quantum computer.
It's going to take a grand vision and a sort of very strategic research program, engineering development in order to reach that goal. But yeah, I think it's at least as hard as the space race, if not much more challenging.
That's because quantum computers have world-changing implications. Cryptography as we know it will change. How we construct pharmaceuticals, forecast weather, or manage large databases will all change.
Some of these algorithms that run on a quantum computers but cannot run on a classical computer are exponentially faster. So there are certain problems that are completely intractable on a classical computer that become solvable on a quantum one.
Combining quantum mechanics with computing isn't a new concept. Physicists like Richard Feynman first started talking about it back in the 80s, but it wasn't until the early 90s when it really took off. Researchers discovered a killer app, some application that could justify spending millions and millions on building a quantum computer. That app was disrupting internet encryption.
Shortly thereafter, there were other algorithms found to, for example, speed up searching unsorted database. That's, of course, a very important problem. And then there has been, since then, a whole explosion of potential applications in terms of optimization, artificial intelligence, machine learning, quantum chemistry, and so on.
And then about 2 years ago, we started to move out of the realm of theory and into, okay, how do we actually build the thing?
There are engineering challenges, just simply manufacturing and controlling the hardware that can run quantum calculation. There are software challenges, just how to code in the most efficient way a quantum computer. And then there are, in some sense, almost philosophical challenges. A large-scale quantum computer is a machine of a complexity that we have never encountered or understood, let alone constructed.
I think there's been kind of a second phase in the quantum evolution recently where there's been a large industrial and commercial investment in quantum computing where we're trying to now, we've identified a few systems in which it's possible to make a scalable quantum computer. And we're really trying to scale this up.
In the past few years, big computing companies have collectively invested hundreds of millions in quantum technology. Startups, research labs, and quantum computing hubs have popped up all around the world. Governments are getting involved too. And here in Australia, the country is transforming into a world-leading quantum computing hub.
Australia's population is small relative to, obviously, the rest of the world. But in quantum mechanics and quantum computing, quantum information science, Australia is leading in many ways. We certainly are punching above our weight. And, Australia can't do everything, but this is an area where we have critical mass. A lot of activity in this city of Sydney, a huge amount of research infrastructure being invested here. And we think it's the place in the world where this stuff is really going to happen.
So engineers have not been involved from the very start of quantum computing. At the beginning, it was really a, let's call it, theoretical pursuit. But as soon as there was the motivation to really go and build a quantum computer, then of course, engineering became crucial. So the construction of the quantum hardware is by and large an engineering problem.
That hardware looks like something straight out of the mind of a steampunk enthusiast.
What you're looking at here is, in fact, a refrigerator. It's a very special refrigerator, one that gets down to a temperature very close to absolute zero. So at this lowest temperature stage here, this lowest plate, we can cool macroscopic matter to a temperature of order 5 millikelvin, so a fraction above absolute zero. So 5 millikelvin is minus 273.14995 C. Pretty cold. Quantum mechanics is very fragile and it's weak phenomena. In order to be able to encode, manipulate information using quantum physics, we have to take the boring classical thermal physics out of the problem entirely. And so we do that with a very powerful refrigerator that gets down to those extremes of temperature.
The amount of power and infrastructure needed to keep these systems running is part of the reason it's such an expensive endeavor.
Playing with nature, the world down there at the nanoscale, at a billionth of a meter, that's not something that you do in your backyard, in your shed with your regular kind of screwdriver. They'll live in very special environments, like the laboratory you see here. It's a temperature stable environment, low vibration, low electromagnetic interference. Not the environment of your pocket. In some ways, I like to think of the building as an instrument. It's a tool that we're using in order to be able to do this science.
So don't hold your breath. There won't be a desktop version anytime soon.
Obviously, people always ask, oh, but how am I going to have one of these in my bedroom? Well, you don't need one. The vast majority of the computations you do in your daily life anyway don't happen in your phone or in your laptop. They happen somewhere on a data server in the cloud. So all that needs to happen is that big data server has a room like this one and a machine like this somewhere that's got a quantum computer in it, and then you connect to it remotely.
But to even get to that point, scalability is a big challenge, as is connectivity.
If you read the popular press, you might get a sense that any day now we're going to switch a machine on. I would love for that to be true, but I think the reality is there are enormous challenges.
We can produce a single or few qubits in the lab, and we've demonstrated that these things have very long coherence times. But in order to scale this up from a few qubit demonstration to the thousands or millions or billions of qubits that you might need to tackle some of the hard problems, you kind of really need to step out of a university environment.
Today we're at that point where we've demonstrated the basic principles, we're starting to assemble prototypes, and the next phase will be those prototypes growing into useful technology.